Hello, welcome, welcome. So, in the previous episode, we got this working and we have a hello world with some numbers. If we run this, then we can see that it's incrementing a counter, but occasionally, if you look at the last digit, it is getting corrupted. So we'll look into that. There was some changes that I made off camera, and you may notice it's mostly over here. So I brought all of the timing parameters out to the very top level. This allows me to have some if-defs inside the top level Verilog that can change the resolution. So I have the timing parameters for 720 by 400. This doesn't seem to work very well with the cheap HDMI capture device that I have, but this resolution here does work quite well. 720 by 480. So that gives us a few more pixels on the side. And the nice thing is the megahertz works out exactly. It's right on the nose for 27 megahertz. So that seems like a nice resolution. One issue though, at least previously, was that that's not supported in digital, but I made PR and got it merged. So in the pre-release, currently the pre-release, perhaps by the time you're watching this video, it will be the full release. This resolution is supported, and here are the timing parameters for that. And the nice thing is 27 megahertz is fairly easy to get with the PLL. So that's that. So we could change these to the timing parameters for 720 by 480 if we wanted to. I'm just going to keep them like that for now, mainly because if I run this, it kind of fits side by side with the circuit a little bit better. If it was 720, it would be a little bit wider. So the other things that I did is I did a bit of optimization. And here you can see that I've got the timing parameters going into the sync circuit and then again, kind of recursively down to where they're needed here. The other thing that I did inside of here is I dropped this down from 16 bits to 12 bits. And this is actually the critical path right here. And the counting circuit is now what's slowing down this circuit. And I'm not sure what I can do about that, but I don't currently have a need to make it go faster. So there's no other changes to here. I thought I might need to change some of this circuitry in order to make it faster, but that doesn't seem to be the case. So that's in there. Surprisingly, this circuit here is not on the critical path, so these comparisons are not a problem. There are ways to get around having these comparisons by converting this into a state machine, but so far I haven't needed to do that. It works fine without being a state machine. So, okay, yeah, I mean, this circuit is a lot simpler, So I dropped down to 12 bits, but this splitter here is expecting 13 bits to turn this into an 8-bit number. So I just sign extended it rather than drop this down to 7 bits. So that's what I did in here. These didn't need to change at all. The rest of the changes are in here. And this circuit is different. In fact, I've got an image somewhere where I can show the old circuit so we can show them side by side. So let me dig that up. So here's the old circuit. Character was having 32 subtracted from it. And then that was going into a multiplexer to select either 0 or the first 6 bits. So this is quite slow, and it was very obvious on the critical path report that this was a problem. I looked into some of the bit patterns in ASCII, and what I discovered was that there's 4 major sections, each 32 long. So the first major section is the control characters. The second one is the numerical digits plus a bunch of symbols. The third one is uppercase letters. And the fourth one is lowercase letters. So if you overlap the top 2 chunks of 32 characters, and if you overlap the bottom 2 chunks of 32 characters, what you end up with is the space being at 0. So then 0 character ends up being the space, which is what I wanted. That was kind of the goal of this circuit here. And now with this new circuit, the lowercase and the uppercase letters overlap. So all I had to do was take the bottom 5 bits and then take the 6th bit and shuffle that down to the 5th bit, if that makes sense. If you have 7 bits, the very most significant bit just gets moved to become the most significant bit of a 6-bit number, if that makes sense. So then you'll end up with 64 characters. The first 32 characters are the same as the second 32 characters in the 7-bit character space, the ASCII space. And then the last 2 blocks of 32 will be the same as well. So this actually just makes it case insensitive. It means if I use a lowercase letter, it'll just be translated into an uppercase letter. It gets a little bit weird with the symbols. You'll get unexpected symbols if you use them, but I think that's fine. At least on the 16 segment font, they end up being gibberish anyway. So that's the change there. That removed 1 critical path. And then you'll notice that there's a lot more pipeline registers in here. That is due to other critical paths. So I removed this critical path and then another one appeared. It was over here, but really these go out to output pins on the FPGA. So they go directly to the HDMI adapter. Now what I was doing is calculating a value and then sending it out to an output pin. And that ends up being kind of a no-no because it's a long distance from where this calculation happens in the FPGA to where the output pins are. Specifically, this calculation is going to be close to where this memory is. So there's the character ROM here, which is in block RAM, and the block RAMs are in the middle of the device, but the pins are on the edge of the device. So it was just taking a really, really long time to propagate the signal from the memory in the middle of the device all the way out to the edge of the device. So adding a set of pipeline registers right at the output pins solves that issue, basically. So the synthesis tools are able to place this output register such that it divides the amount of time that it takes to propagate the signal all the way out to that pin. So this cut that critical path in half, actually, and then it just disappeared from the timing report. But then there was another issue that was going into the address of the block RAM. So that became the bottleneck here again. And so I added another set of pipeline registers, and that pretty much eliminated the timing issues entirely from this circuit. The timing issue, like I said, is now the counter in the sync pulse generator. All right, so that's pretty much it for any of the changes that I made. So what we have is a set of modules that we can use to build basically a front panel using this. The only thing that I would kind of like to have is the ability to display LEDs or what look like LEDs. One thing that I could do is add a circle to the font. It will be a monochrome circle, so I don't know how much that would be interesting. One thing that I could do instead is just use the enable signal on a text display to basically blink the text for whatever signal I'm trying to display. So I think that's what I'm going to do for now. And in the future, maybe we could add sprites potentially to this so that we could display something that has more vibrant colors and turn that on and off. That'd be neat. For now, I'm not going to do that. I have been kind of thinking about how I would do that, and I need to build basically a tile map system, probably. And I'd like to do that, but I think I'm going to reserve that for the future. I'd like to get back to the CPU more quickly. The other thing that is going on here is we have characters being corrupted. I think I figured out what the issue is. And the issue is that this line right here isn't going to solve the problem. It's because this goes low each row. So what we're getting is corruption because the thing that we're trying to display is changing as it's being drawn on the screen. So the solution actually is just to add a busy signal. And actually this is it right here. If the current string is on screen and the Y signals are active, then we want to inhibit any display update. So it's easy enough to do that. Output, just put it here, I guess, or about right there. And we'll just call this busy. And then we need to route the busy signal out to a wire here as well. And if we just route this, so then it'll update only if it's not busy. And we could invert the polarity of this, but most modules are not going to need it, so I'm just going to leave it as busy. All right. So the corruption should be gone, but it's kind of hard to tell since it's going so slow. So let's get it to go faster again. Or actually, we can just leave it as 32 and we can just adjust which bits we're looking at here. And we should no longer get any corruption, and it doesn't look like we are. So awesome. So that's fixed. So I'd like to integrate this into the main circuit, and that's kind of the point of this video, and I've rambled far too long. So let's get right to it. I think actually we can copy most of this. Just trying to decide how to do this. I think probably what we want to do is separate out these modules. Yeah. I'll just put them there for now. Then in here, we need inputs and outputs for those. Okay, it still works. Let's keep going here. So it's probably just this itself that needs to be moved into the other one, and then we can build new modules for this stuff. So we have this. What I kind of like to do is make the VGA module just a separate thing, and we can put inputs and outputs on it. I think that should work. Well, let's just, we can always change it. New embedded circuit. Let's call it, actually, call this VGA Front Panel. And there's going to be another layer we'll call okay, so what do we want to display? We want to display the op, definitely, and probably the register values. So if we're looking at this, the register values are over here, and probably we'd put the display right here. What I'm going to do is I'm going to put this into layout mode. All right, let's do the program counter first, and then the other ones are going to be very similar. So actually, we could almost have a separate module for those two. Yeah, we could have an embedded circuit that's just this. You know what? I'm going to do this differently. I think this one is the one that has everything kind of laid out a little better. So what I'm going to do is I'm going to make this only 5 bits. And then I'm going to make it 6 bits going into these two, but they're going to get a different set of bits. So going into this one, it'll get 0 as the least significant bit, and this one it'll get 1. And that'll avoid having to do addition. I'm going to make them have a common background color, but the foreground color could be different. Foreground, lab, foreground. And if you think about it, the busy signal will be the same for both of these, since they're always on the same row. This is kind of starting to get pretty messy. Very messy. Need more room. So I'm going to hard code a space between the number and the label. So the label will only have up to 3 characters, but I think that's fine. Oh, I think I see what's wrong. That background is unfortunate, but we should be able to change this. A little bit of lag because the simulation is so slow. Okay. I'm not sure I like the contrast there. So let's see. That seems better. Okay. Hmm. Okay. And we should be able to step the processor and we'll see our registers updating. So that's nice. Be nice to be able to turn the VGA display off. So let's quickly do that. The easiest way is to gate this signal, and in the FPGA we don't want to do that. But the FPGA is going to have just this subcircuit in it, and the clock will be coming straight in. So we'll gate the clock at a higher level. Well, actually we can just insert the circuit here. If we don't clock the VGA monitor, then it won't pop, so you won't have any display. That's big. So now it won't display at all. But if I turn this on, then it should pop the display after a moment. There we go. So we have the beginnings of some VGA blinking lights. I just had a thought. There's nothing saying that we can't have a separate clock for the VGA. So this one could run at, say, 5. And we could have a completely separate clock for the VGA. Let's do that. I'm going to call this DC for dot clock. I'm going to clean this up later. Oh, and we're getting corruption. Probably because now we're crossing clock domains. Well, the fix is pretty easy. It's just adding a register into the label num subcircuit. So I can do that later. Cool. So thank you very much for watching. I hope you have a great day. Bye.